Lab 4 Oscillations. The purpose of this experiment was to determine if a spring mass system adheres to the energy principle by analyzing the change in energy, both kinetic and potential, of the system oscillating in an arc. The system follows the energy principle as the total change in energy is zero due to the absence of external work or heat transfer. The energy principle states that the system's change in energy is equivalent to the work done by the surroundings added to the thermal energy exchanged with the surroundings. In this experiment, the system is the mass, the spring, and the earth, and the surroundings is nothing, meaning that the change in energy of the system should be equal to zero. Additional equations that we will use are the equation for kinetic energy, gravitational potential energy, and spring potential energy. The net force acting on the system includes the individual force of the spring and the gravitational force. Newton's second law, also known as the momentum principle, states that force is equal to the change in momentum over the change in time. This is also equivalent to mass times the change in velocity over the change in time, which is the same thing as mass times acceleration. Using the formula at the top of the slide, we can derive the velocity update formula as shown. Using the provided video of the spring mass system shown on the left, the motion of the mass was tracked using Tracker after the video was imported into this system and calibrated with the provided initial conditions. We place the origin at the spring attachment point to simplify our calculations. The graph on the right shows the amplitudes of the y-coordinates position versus time graph, as well as the amplitudes of the x-coordinates position versus time graph. We notice that for the y-coordinate, the amplitude decreased over time, likely due to the force of gravity acting on it. This relationship was not observed in the x-coordinates position versus time graph. Using the starter code provided in GlowScript, we simulated the initial model conditions as follows. The mass of the block was provided in the pre-lab video. The initial position was determined by the first data point in the tracker analysis. The initial velocity was equal to the zero vector since the mass was released from rest. These were constants that were used in the calculations. The spring constant and the relaxed length of the spring were provided in the pre-lab video, and 9.8 is the gravitational constant close to the Earth. We needed to include formulas for the energy calculations. The formula for the length of the spring is the position of the mass minus the position of the spring. The unit vector is the length of the spring divided by the magnitude of that length, and then S is equivalent to the magnitude of the length minus the relaxed length. And these are the equations for kinetic energy, gravitational potential energy, spring potential energy, and total energy. These initial energies are equivalent to the previously stated formulas. These are the formulas for the gravitational force, the spring force, and the net force, which is the sum of the gravitational force and spring force. These are the position and velocity update formulas previously derived. And these are the formulas for kinetic energy, gravitational potential energy, spring potential energy, and total energy, as well as the change in all of these individual energies. This animation shows the blue ball, which represents the computational model, and the red ball, which represents the experimental model. To compare these models, we notice that the motion is generally the same towards the beginning of the motion. However, over time, more deviation in the motion occurs. That's likely because this system is not truly isolated, and there is work happening on the system by external forces like drag. Potential sources of error arise from the fact that the system of the real-world model is not truly isolated, and there could have been errors using trackers such as inaccurate tracking of the center of mass. While there are non-zero energies acting on the system, the overall change in energy is zero, meaning that the energy principle is satisfied. The period of oscillation for the x direction indicates that there is a time interval of 1.65 seconds, and when these calculations are done to calculate the spring constant is 5.82 newtons per meter based on the x direction graph. However, for the y direction graph, the period of oscillation takes place in 1.52 seconds. So when the spring constant is calculated, we get 6.83 newtons per meter. Calculations from both directions yield a different spring constant. Because the x-coordinate spring constant was used in the calculations, the deviation with the y direction spring constant likely caused some inaccuracies.